welcome everyone. We have Alessondra Springmann here with us today, who's a data analysis observer and planetary radar astronomer from Arecibo Observatory in Puerto Rico. And she has a very interesting and fascinating presentation that will involve avocados and potatoes.
All right. Hi, everybody. Alessondra. Thank you for having me. You should ask lots of questions. It's a mechanical engineering department. I don't necessarily expect you to know a lot about asteroids. Don't necessarily expect me to know a lot about engineering, but I'll try to give you a presentation that's accessible and interesting. So please stop me if I'm saying things that make no sense, or if you have questions, it'll be great. I know you. All right. So I work at Arecibo Observatory. I'm a data analyst there. I'm an observer. So Arecibo Observatory does a couple of things. We look at using passive radio astronomy, where we listen for radio waves from galaxies, from extragalactic structures. We also do Ionosphere, which is study of the upper ionosphere with radar as well as LIDAR. And we also do radar astronomy, where we look at objects in the solar system. And so I'm going to focus mostly on that today, because that's my area. So this is a radar image of an asteroid called 1998 QE2. So if you're paying attention to the news earlier this year in late May, early June, this thing came by Earth. I have a few more images of it. It's 3 kilometers across. And that little streak that looks like a bird has dropped on it is actually a moon. So asteroids have moons, and we'll be covering that as well. Okay, so near-Earth asteroid overview. There are about 500, 600,000 asteroids we know about these days. Most of them hang out in the area between Mars and Jupiter. So this is sort of a view of the solar system in the last couple of days, looking down. The big thing in the middle, that's the sun. The planets are not to scale on here. The orbits, however, are to scale. But the dots themselves are. The asteroids, the objects are much, much smaller than you would see here. The sun's in the middle. You have Mercury, Venus, Earth, and Mars. The green asteroids are asteroids that are generally spend most of their time between Mars and Jupiter. They're in the asteroid belt. And then the red ones are near-Earth asteroids. So they're ones that come in close to Earth. 1 AU, have perihelion of about 1 AU. So some of these could be potentially hazardous. Some of them might hit Earth. That does not inherently make them killer. It just makes Earth in the wrong place at the wrong time. So we're going to be looking at some images of these asteroids. So why do we care about asteroids? Why do we care about asteroids? Anyone? They can hit us. Okay. We're at the Colorado School of Mines.
They have no.
They have metals. They have water. Metals, not so much, but they can be used for space exploration. The economics of mining platinum group elements off of asteroids, it doesn't quite work out yet, but I do look forward to the day that it drops the bottom out of the Chinese rare earth metals market. Okay, so asteroids, this is where they are, this is where we're going. The discovery rate of asteroids. So we've observed about 10,000 near-Earth asteroids so far since they started being discovered in the 1960s, 1970s. And so the pluses are just near-Earth asteroids discovered, and the boxes are near-Earth asteroids observed, are the ones observed with radar. So this is near-Earth asteroids overall on this axis, and this is near-Earth asteroids observed with radar. So last year, we've observed about 300 near-Earth asteroids overall with radar. So it's a significant portion of the population. And radar sort of has its own set of biases, not biases, but we observe everything that comes within about 1/10 of an AU from Earth. An astronomical unit is a distance from the Earth to the sun. So anything that comes close enough, we look at. It's a telescope working. So why study asteroids? They can come hit us. They could hit us, possibly. General wisdom is that an asteroid impact wiped out the dinosaurs 65 million years ago. What's the difference between us and the dinosaurs? We have a space program. They don't. No. Mitigation, understanding what asteroids are like, what they're made of, so that if we do need to deflect one, we can. What size drill bit do you tell free flow spring? You've seen Armageddon? Mining, asteroids have resources, water, metal, potential for using this full spacecraft to explore the rest of the solar system. Really hard to get stuff off Earth. MGH is a real pain. Potential energy. So if you can get your materials out in space, it's a lot easier. Planetary Resources is working on this. There's actually a couple of asteroid mining companies right now. One company, they're not. 2 companies, it's an industry. And I know Planetary Resources is hiring interns. I'll send Doug information about that if you're looking for a summer gig. So asteroids. So we have lots of images of asteroids. Most of these images are from space missions. And space missions cost a lot of money. $500 million, $1 billion. Each of these images cost on the order of millions and millions of dollars. And you can see there's a whole bunch of different asteroids that have been looked at by space missions. And some are really big. So this one's 130 kilometers across. Named from Bossuyt. This one's huge, and the rest are to scale and also in terms of brightness. So asteroids are really varied. Some are really bright, some are really dark, some are big, some are small, some are elongated. There's a whole menagerie of shapes. So every time you go and see an asteroid, it's different. But they do have things in common. So all these are really expensive. Millions and millions of dollars to get these images. Can we do this more cheaply? Yes, we can. So Arecibo Observatory, we observe asteroids with radar. And I'll get into the details later, but these images are maybe tens of thousands of dollars each. And the largest cost is diesel fuel for our generators to generate power, and then personnel after that. So for orders of magnitude less, you can figure out what your asteroid looks like, its growth shape, size, and a couple other properties, even surface properties and even mineralogy, just by transmitting light at an asteroid and listening for echoes. But radar is totally awesome. It saves you a ton of money. So Arecibo Observatory, it's great. Please visit in Puerto Rico. Come down and visit. We're open all the time. So it's a big 1,000-foot diameter dish, 305 meters across. What's 305 meters times pi? 1 kilometer. So there's a 1 kilometer running track going around the telescope, which is kind of neat. It's got a dome and a platform that hangs 500 feet up in the air above the telescope. And so there's the big Gregorian dome, has all the radar and radio astronomy instruments in it. And then there's an antenna on the other side that you can't see in these images. There's a catwalk that goes up there. It's pretty neat. Our colleagues at the Jet Propulsion Lab in Pasadena use the Deep Space Network telescope out at Goldstone. Doug and I went out there many years ago. And it's a 70-meter telescope. It's a 1-acre size telescope. And the whole thing sits on a thin layer of oil in order to rotate. So Goldstone is steerable. Arecibo is not. Arecibo is bigger than Goldstone, and we're at larger sensitivity, but because Arecibo is fixed in the ground, we can only point 20 degrees off Venus in either direction. Goldstone can see things for longer than we can, but we're more powerful and we're much more sensitive. So they're complementary instruments. They can get much more coverage of an asteroid over a longer time, but we see a lot more detail. We can see boulders on rocks and things like that. So our wavelength is 12.6 centimeters. Theirs is 3.5. They're at a higher energy. They're an X-band, we're an S-band. That means anything to spacecraft people. If I start talking in bands, tell me to shut up. This is Arecibo Observatory. This is the view outside of my office. It's kind of great. So here we have this Gregorian dome, and here we have an antenna. So antennas focus one frequency really well. But for radio astronomy, you want a wider band of frequencies that you collect. So what we do is this dome actually has a series of mirrors inside of it that focus radio waves to a point. And when you focus your radio waves to a point, you can actually get a much larger bandwidth of observations. For radar, that doesn't matter because we transmit at 2.4 gigahertz, right around the same range as your microwave oven or your cordless phone or your cell phone. But for the radio astronomy, they want a much wider bandwidth so they can see many more features. So we don't have wireless at the observatory. We don't have cell phones. We don't have microwave ovens. We don't have DC motors. When I lived on site, I had an AC motor hair dryer. My food processor had to be checked for RFI. Radio frequency interference is a huge pain. And all these grad students visit from electrical engineering, they're like, we don't understand why we can't use our phones on site. Like, dude, we can detect your cell phone on Mars. If you come visit, don't expect to use your phone. Again, here's another view of the observatory. So this is a Photoshop job done by one of my colleagues just to show the size of the observatory and an asteroid. This is DA-14 that came by on February 15th earlier this year. And so we didn't see it because it was too low in our sky, but we could have seen it. And it just goes to show you that we regularly look at asteroids that are smaller than our telescope, which is kind of neat. So how do we transmit signals? The power grid in Puerto Rico is pretty unreliable. It's part of the U.S., a territory, or a colony, depending on what you want to say. But power goes out pretty regularly. So we have 4 diesel generators that create 2 megawatts of electricity. This is the generator room. You have to go down there and switch on the generators about 40 minutes before you start observing to warm them up. And then we have a power supply. It's the simplest circuit in the world. You know, your full wave bridge rectifier, 4 diodes, except there are actually 12 diodes that sit in a giant oil bath in a structure that's about the size of 4 of these tables. And, oh yeah, it's 65,000 volts at 33 amps that produce 2 million watts with the power supply. So this might be the simplest circuit in the world, but you're dealing with just, I mean, so I built this when I was an undergrad. You're putting your little diodes in series, and they have their cute little suicide packs that they all blow out. But this is a little more complicated than that. You have to get the thing out of the oil. You have to wait for all the oil to drip off. You have to clean it off. You have to replace your diodes, which are $500, $600 each. So this is a new voltage regime from what you do in labs. So it's kind of neat that it's very simple, but it's also very complex at these higher voltages. And so we transmit 65,000 volts along a high voltage cable that goes about 500 feet out to the center of the telescope. And they power these things called cyclotrons. Has anyone been to California, seen Stanford Linear Accelerator Center? They have a whole gallery of these things. So they're used for, they accelerate electrons back and forth. So they have a cavity inside, you put a high voltage in them, and you emit waves, radio waves or X-rays, as they do at Stanford these days. So we have 2 of these. They're each half a megawatt-ish, and combined you get 1 megawatt. So we dump 1 megawatt of waste heat, so we put 1 megawatt into these cyclotrons. The other places they use cyclotrons, weather radar, and who's wearing sneakers? Somehow your sole of your sneaker has to get fused to the shoe, so you can use microwaves like these cyclotrons transmit to do fusing things like that. Cyclotrons are totally opposite. But because we have 10 to the 7 power gain, we have a 1,000-foot dish, we are actually transmitting 20 terawatt isotropic equivalent. So you're really not allowed to hang out in the telescope area when you're transmitting. It's kind of cool. But you don't want to, occasionally you have to go straight for out of the secondary dish in the dome. So this is one of the cyclotrons actually in the transmitter room. You can be in the transmitter room while you're transmitting that state. And it's not ionizing radiation, so you can be. You're just going to get heated up. You're not going to mutate. So you have 2 of these things, and they're cooled with actually a home brew system, quite literally a cooling system from beer making that puts 300 gallons of water a minute to the system to keep it cool. And we also, and so dumping 1 megawatt of waste heat is huge. It's kind of hard to do that. And so when the flow meter, this is a very complex system. You've got the cyclotrons, you've got the high voltage cyclotrons. You've got to make sure the current's okay. You've got magnets inside the cyclotrons, so it's your electron beam. Then you also have the cooling system, and you have sensors everywhere. And a lot of these sensors have been there for 15 years, 20 years. Some of them work, and some of them, don't work. You sort of bypass these sensors. You jump for things that you really shouldn't jump for. They're like, well, this isn't working. Well, we know we jump for that. If you know any high voltage engineers who are looking for jobs who like troubleshooting this sort of stuff. We also have, this is an old DOS program that monitors the cyclotrons. So you've got all these various interlocks. Some of them get jump proof, some of them don't. You've got various high voltage systems. You've got the power supply. You've got the transformers. And so, is this one actually not working, or is this one working? So it's very seat of the pants sometimes, but it all works out. All the high voltage status indicators. Cyclotrons have filaments, just like light bulbs. They're sort of light bulbs, except for radio waves. All right, so radar basics. We transmit light at an asteroid, and we get it back. So we've gone through the transmission aspect. We've looked at the generators, we've looked at the power supply, we've looked at the cyclotrons. So we transmit waves out, they bounce off an asteroid, and then they come back. How do we collect those waves? So waves get focused into the dome, and they come into these receivers. So these receivers are, most of the time, I come from optical astronomy, and I spend a lot of time looking at cameras. They have sensors, just like what's in your digital camera, a little different. Radio wave receivers are just black art. And you transmit, when you create a linear polarized wave, you have to somehow turn that into a circularly polarized wave. And they actually refer to the device that does that, the turnstile junctions, as magic devices. And so you receive a circularly polarized wave, you have to turn it into a linearly polarized wave on the way out. There's just this is completely not my area, but I think they look really cool. And there's a whole, this is all on a lazy Susan. There's about 8 or 10 instruments experiment you're doing, whether you're doing radio astronomy or radar, we transmit. We have a transmitter right next to a receiver. And it takes 8 seconds to switch from transmit to receive. So any object that's closer than 8 light seconds away, we can't do. Or we have to transmit, and another radio telescope has to receive. We do by static receiving occasionally. So the radio waves go through the receivers, and they come to the actual receivers, and they go into the instruments. And so they're cool, because in radio, we're limited by thermal noise. So you talk about thermal noise equivalent, so it's Boltzmann constant times your temperature in Kelvin. And so most of our instruments are cooled to around 25, 30 Kelvin. So that is our limiting factor. So we use liquid helium and a lot of these to keep our instruments cold at all times. Otherwise, the noise from heat will simply overwhelm your signal. And we actually get that when when the object is focused at the edge of the dish, you start getting signal from the jungle, thermal background from the actual ground around your telescope. And so it's really best to observe things when they're straight overhead. But once we start getting to the edge, we move a lot. So everything's kept really cold. Helium compressors. We lost our cryogenics engineer who just went to go work at the National Radio Astronomy Observatory. And he was supposed to start right when they first had the furlough and the shutdown at NRAO. So I feel really bad for him. But if you know of anyone who really likes cryogenics and keeping things cold, I'm hiring. Not even enough. So we have helium compressors all over the place. It's very loud. There's also huge fans for blowing hot air and heat off of the electrons themselves. It's very loud up there. So here are the fans inside the dome. The dome's about 60 feet tall. And you can sort of see the structure of the platform of the telescope here. There's a rotary joint in the center. And then you've got this circular track, and you've got this arm that the dome is mounted on. And the arm rotates around. And then the telescope dome can move up and down the arm. So it can point in elevation. And then you have the arm itself rotate. You can pretty much point anywhere in your 40-degree cone. And this was early one morning. It was great. I used to live on site at the observatory for about 8 months. And it was pretty cool, because you could just wake up at 5, 6 a.m., you have friends visiting, let's go to the telescope. Take a lot of photos. It's really neat. So we receive the signal. The signal comes into your radio receivers, it's cooled, and then it comes down cables to the control room. So really, Arecibo Observatory is the world's largest volt meter for measuring voltage. And until you measure things with power, you haven't really measured them. So you can torture your signal by amplifying it, filtering it, attenuating it, putting it through all sorts of various filters in the control room with BNC cables until you're finally ready to measure it at the very last second. And then you put it into a spark station that's about 20 years old and finally measure your signal. So we do as much processing and hardware as we possibly can. So as soon as you measure the power, you've observed it, and you lose information once you start reprocessing it there. So first showed up at the observatory, and my boss was like, okay, this is how we cable, and I've really never seen anything like this. The first things come out of the down converter, and it's all pre-calculus. It's all trigonometry. It's all multiplying signals together, subtracting signals, dividing signals. It's actually really neat. You just have all these filters to make sure you get what signal you want out, and lose power line hum and harmonics from radio stations and things like that. And eventually you get a signal. But this is also the part of the control room. It's some very vintage hardware. It's kind of neat. These ones, the transmitter for the atmospheric radar actually uses knobs to adjust things still, rather than a keyboard console. So things are very vintage, and somehow it all works. The Doppler. Let's start actually talking about signal feedback. Has anyone gotten a speeding ticket? I got pulled up for speeding once I got out of it. So your happy police officer, sheriff, highway patrol, he's sitting there with his radar gun, and he transmits at one frequency. And your car is moving with a certain velocity. And when his signal bounces off your car, and he receives it. And the instrument says, okay, this velocity that I got back, the frequency I got back, has been shifted by a certain amount. Well, we can do really simple math and figure out what the initial velocity is of the object. So just by looking at a change in frequency, you can find out how fast something is moving. So most optical astronomers look at asteroids moving across the sky like this, just in the plane of the sky. And And so they can see how it moves over a couple of nights, but they can't tell if the asteroid's coming closer or moving farther away. So radar is trying to give asteroids speeding tickets, saying, are you moving towards me? Are you moving away from me? And you can use that information for improving orbits tremendously. So the math is really simple. There's no linear algebra, there's no differential equations, it's just trig and algebra. It's great. So how does this actually work? So we transmit a continuous wave. I believe it's right-hand polarized, bounces off the asteroid, and it comes back left-hand polarized, if it bounces once. If it bounces off a perfect mirror, transmit in one polarization, you get back the opposite polarization. Asteroids are rocks. They're not perfect mirrors. So you actually get some of the same sense polarization as you transmit it. And if you look at the opposite ratio of one polarization to the other, you can actually get an idea of surface roughness. So some asteroids are smoother, like potatoes. Some asteroids are more rough, like avocados. And if you look at sort of the surface roughness of an asteroid, you can actually make some assumptions about the mineralogy of the asteroid. What is it made of? Is it more metallic, or is it more stony? But asteroids don't come with little stickers on them saying, yes, I'm a Haas avocado from Safeway, or I'm a Florida avocado. So we have to make some assumptions. We have to look at data from space missions, data from optical telescopes. But it's a fun puzzle to try to put it all together.
So metallic is rubber than stone.
Depends also on crystal size. So some minerals will be larger at certain wavelengths and some won't. And sometimes it has to do with the strength of the material, things like that. So here, just like with our cop car, putting radar in you. So you transmit one signal, and you get the signal you get back is shifted a little bit. And so you Fourier transform the echo, and you see you get the spectrum, and from that you can figure out rotation rate of the asteroid and also how big it is. So here's this is spectra of an asteroid. So if it was just a perfect sphere, you'd get a Gaussian back. But it's not. There's some roughness. And those two spikes actually are moons. And since the moons are moving a lot more slowly than the rotation rate of the asteroid, they're not as spread out in Doppler space. So I bet in theory, if you're driving fast enough, your signal would be, and someone's checking your speed with a radar gun, the signal would be so spread out they wouldn't be able to tell how fast you're driving at all, but you'd have to be driving really fast. So with asteroids, the faster they rotate, the more they get spread out in Doppler space. And the moons don't rotate very fast. They're tidally locked to the asteroid, and so really you're looking at the rotation rate. So if the asteroid rotates once every 4 hours, and the moon rotates once every 2 hours, you're going to see the moon's Doppler spread compressed quite a bit. So that's how you get those spikes. Okay, so with asteroids, again, what do we measure? We can measure their orbital distance and their velocity with radar, because we know when we transmit it, and we know when we get the echo back, which is kind of cool. So we actually will sometimes transmit a coded signal, and so we know when that code left the telescope, and so then when that bit comes back, we say, aha, that asteroid is that far away. And since we're doing nanoseconds, microseconds, so we can know where these asteroids are at about 7.5 meters. Kind of cool. So if you know how long it takes for your echo to get to the front of the asteroid, and then back, you can actually get the size of the asteroid, the size and shape. The Doppler dispersion is the rotational velocity, and you can also get an idea of the shape. And then scattering properties give you an idea of the surface roughness and also mineralogy. And we don't just do asteroids, we do also other objects. We do a lot of astrometry. NASA, everyone else in astronomy is freaking out about money right now. We're not, because NASA has been told we should go find these near-Earth asteroids and figure out if we might get hit. And so we do orbit improvements on these near-Earth asteroids. We do a lot of astrometry. How far is it away? How long does it take the radio signal to get back? And we can improve orbits by orders of magnitude in terms of predictions, and we can extend predictions out decades, if not centuries, for what these things are going to be. Because sometimes when you first observe an asteroid and you don't get enough observation, these asteroids can be lost. And that would be bad if they were come back magnitude. We also do radar images, like I was showing you earlier. So this is really weird. So imagine you've got your asteroid rotating like this. And you transmit radar like this to your asteroid. Now, you're not going to be able to tell if a feature is in the north or in the south when you finally do collect the echo. So this is the redshift side moving away from you, and the blue shift side moving towards you. But if you look at this in Doppler space, you're not actually going to be able to tell which features are in the north, which are in the south. It's actually like taking your potato or your avocado, smushing it flat and just looking at that signal, or cutting up your potato with a little bit and sticking them all together. The way you resolve that ambiguity is you look at the asteroid from a bunch of different vantage points. And you also get optical astronomers look at it, or you try to look at it over the course of a few years every time it comes by Earth from different angles. So maybe you'll see it from the equator on one year, maybe you'll see it from a little further up. That can help resolve the ambiguities in the shape and see if features are in the north or in the south. And the layout Doppler images give you the size of the asteroid because you know how long it takes for the radar wave to get to the front and also get back the asteroid. And from that you can get a pretty good estimate for the size. And there's a lot of Fourier transforming here. Pretty much let it work and run thousands and thousands and thousands of Fourier transforms a day. It's great fun. But yeah, we have 7.5 meter scale of this asteroid. Kind of crazy. So comparison to spacecraft data. Like I said, spacecraft cost billions of dollars, if not billions of dollars. And so really inexpensive to get sort of, even from the radar images, just an idea of what the asteroid would look like before you get there. And with the shape modeling we can do, we can get pretty good. And it also can help your space agency plan where to land on the asteroid. You want to land on one of the ends, you want to land on sort of the neck of the asteroid, Ionosphere. So we also do the moon. We're not biased, we do everything. So you can get surface reference maps of the moon. You can also sort of get an idea of where there might be ice and some of the craters on the moon. So we collaborate with a spacecraft called LRO, Lunar Reconnaissance Orbiter, and its radar broke a few years ago, but it can still receive signals. So we transmit, and LRO flies off to the side and receives, and it gets actually backscattered from water ice or projects like that. So it's sort of, I wouldn't say it's fortuitous that the radar broke, but it allows us to do some really cool experiments. We transmit, they receive, the other telescopes receive at once. So you can get the backscatter, and you can also get just the return signal. And you also know what we transmit. We actually transmit little chirps of the moon. So I put some Twitter, I'm chirping at the moon this morning. Mercury, we predicted water ice on Mercury in craters. Just sort of neat. And permanently shattered craters, holes. Mercury is the closest planet to the sun. I don't want to live there. But there's water in the craters. How neat is that? We can do so many things with radar. Venus. We didn't know the rotation period of Venus until 1964. And radar measurements of the surface finally figured out, okay, we'll rotate this back. But to not know the rotation rate of a planet that we've been observing for, since humans first looked up the sky until 64, I mean, radar's pretty neat.
How fast does it rotate?
I don't remember, but I'm totally happy to look that up. Mars, you can get surface reference maps. Elysium, everyone see that movie? But asteroids. So asteroids have a whole bunch of shapes. So my favorite main belt asteroid is Cleopatra. It's the size of New Jersey, and it's made out of metal, and it looks like a dog bone. I like the dog bone the size of New Jersey. What? We have some other ones. I don't think I have the roast chicken one in here, but you have spherical asteroids, you have irregular asteroids, you have asteroids with moons, you have ones that rotate, in the order of minutes, ones that rotate on the order of days. It's a very diverse population. We support all types in the asteroid community. Cleopatra. These are the color indicates both. So red is 40 degrees, and then the orange is 0 degrees. So this is a shape model from radar. It's not sent a spacecraft to the asteroid yet. And because it's big enough, even though it's pretty far away, we can do pretty good studies of it. YU-55 is spherical, and get some nice images of it. So this asteroid has a really interesting shape, sort of this odd tetrahedral thing. So you look at these radar images, what's going on here? But you can do these inverse models and sort of get an idea about the shape. 5 minutes. Once every 5 minutes, what, has it shed all this material on it? How does it bounce like that? There are so many questions to ask with these asteroids. Contact binary. A lot of asteroids look like peanuts. A lot of asteroids are stuck together. My office mate worked on how do you do the tidal interaction such that if you had two asteroids orbiting each other, that you would get these contact binaries stuck together. HW1, I actually found a sweet potato at the grocery store that looked just like this asteroid. And someone made a 3D model of it and put a little asteroid texture on it. And try to make radar data out of it and flip it in to our colleagues' data sets to see, they get very confused. But there's a lot of these things like that. And they're about 14% of the Earth's asteroid population. We also look at comets. This helps spacecraft know where to go looking. And so Deep Impact went by this asteroid in 2010. Google Impactor at it looked at the ejecta. Deep Impact has been flying by other objects since then. It's gone to a couple other asteroids. It's going to go to 2002 GT, which we were hoping was a binary. We had inconsistent data from Arecibo, and then there was some unsigned in overflow issue on the spacecraft. You can't talk to it anymore. So make sure your spacecraft are radiation hardened. Make sure you check for faults. Make sure you build things that are robust and reliable such that they last for 3-4 years after the spacecraft does its primary mission, because you never know when your spacecraft is going to be reused for something. So in 2010, NASA flew by it for Deep Impact. So no, it impacted Temple 1, and that was years before. So Deep Impact has just been reused and used and used for looking at other objects. It's really neat to get these images and see. But we knew what the shape was ahead of time, so that really helped them plan a mission in the orbit. Binary. So we have the contact binaries, and we also have real binaries. So you see these little moons, again, they're compressed in Doppler space, and there's a huge variety. Sometimes they're equal mass binaries, like Hermes, orbiting a center of mass, a common Berry center, and sometimes they're much bigger with a smaller moon. So we'll get into more of those. This is KW4. This is everyone's favorite near-Earth asteroid because it looks like a muffin or a top. It's got an equatorial ridge, which I hear people develop too as they get older. And it's got a cute little moon, and we actually are able to get a shape model of the moon. I'll sort of get an idea for a shape. It's not just a sphere. So here we have radar, synthetic radar images, and here we have the actual shape model. So this is what the radar would look like as the asteroid is actually rotating like this. So when the moon is between us and the asteroid, it's furthest away from the asteroid in the radar images. And then you'll see the moon disappear behind the asteroid in the late Doppler space over there as it goes over there. This is, I still have issues wrapping my brain around it. I think my bosses do too. Radar is just completely a dark art. But
The piece that just came out in the asteroid company.
this is old. This result is a couple years old.
I mean, the moon is something that came out.
So the idea is that you get this asteroid spun up, who knows how it gets spun up, and the material slides off the equatorial ridge and coalesces into a moon. And then there's also some ideas you can capture these moons. So we think that the moon, if you're able to put a spacecraft there and actually resolve the moon relative to the asteroid, you would be able to see, okay, these are made out of the same stuff. Or that it would be made out of the same stuff as the equatorial ridge, and that the poles of the asteroid would be made out of different stuff. And you can actually, using optical telescopes, if you know when the moon is going to go in front of the asteroid and eclipse the asteroid, and then the shadow of the asteroid would eclipse the moon, you can predict those mutual events or those mutual eclipses. And you can actually use that to make a brightness map of the surface of the asteroid and the moon. And you can make some inferences about composition that way. And it's amazing, with an optical telescope, you only resolve the asteroid and its moon at the point of light. You don't see the moon at all because they're so small, they're so close to each other, they're so far away. There may be a couple kilometers away from one another. But the fact that you can actually do this is amazing. And you can get so much information just with your optical telescope. The binary. When you get mutual events, you can watch the secondary, the moon enter the radar shadow. And if you can time these things, you can use this for improving your orbit of your moon. You also have triple asteroid systems. What? How do you get two moons in a stable orbit around something bigger? Some regularly flying by planets and getting perturbed. So the first time they're like, no, there can't be triple systems. Yes, there are. So who knows? What? Anyway, no Arecibo data, and we think it might have an equatorial ridge like KW4. You can see this little moon. And you can kind of see there's some features, there might be some craters, there might be some bright spots. So that will be useful when we finally get a shape model of it. And the mutual orbit of the moon. So this moon's really cool because it looks actually, if you're going to do the model of it, actually looks like a piece of candy corn with a notch missing from it, which is really neat. We were able to get a mutual orbit of it, and we're going to be able to make a shape model of it. Very interesting. And so these are goldstone images of the moon. You can see it's actually got a shape. It's not just a sphere. So when we run inverse models on it, actually try to do a model, it's going to be totally awesome. This is an orbit solution of the moon. So it's got a second major axis about 6 kilometers. The moon itself is 3 kilometers across. And it goes around the asteroid once every 32 hours. So a collaborator did this, and said, you should put error bars on this plot to give us the data. I'm like, don't loop. The error bars would be smaller than the dots on this plot. So it's a very circular orbit. We know it pretty well. It's a little terrifying how well the model fits the data for this moon going around the asteroid. So I think that's fun. And the other thing is, since we know the size of this asteroid and we know the orbit of the moon, we can make guesses as to the mass of the asteroid because of Kepler's third law, a high school math, and so you can actually get the density of the asteroid. It's about 1 gram per cubic centimeter. What? So does this thing kind of like styrofoam? Does it have a bunch of particles stuck together? Is it batched? Is it sort of is it a rubble pile? Is it things that have big, does it have a lot of porosity? It's obviously made out of some sort of stone, and looking at thermal spectra of it, we guess that it's made out of some sort of very dark, primitive meteorite, asteroid material. It hasn't been thermally processed. It doesn't have evidence of olivine or pyroxene. It doesn't have mineral evidence. So it's just sort of this flat, dark, carbonaceous stuff. So what's this made out of? We have density estimate, which is very cool. It's hard to make the estimate the density of objects unless you send a spacecraft around them, or unless they have a moon. So maybe it looks like that KW4 muffin object. For the secondary, we have an orbit solution. And since we actually are going to be able to know the shape of the moon, we're actually going to be able to estimate, or at least constrain, the effect of non-gravitational forces on the station. So once upon a time, there was a Russian engineer named Verkovsky, and he predicted that asymmetrical thermal re-radiation from satellites would change the orbits of the satellite. So you have a daytime side, a nighttime side, and they heat up non-uniformly on your spacecraft, and will actually give the spacecraft a thermal torque. And that can either cause the orbit to decay or move further out. And you can also cause the asteroid to change its spin axis orientation due to non-uniform thermal torque, which is pretty neat. And in binary systems, you have it even more magnified, and it has to do with tides. So because we are going to have a model of this moon, we're going to be able to constrain those non-gravitational effects in the system, which is pretty neat. Because mostly when you think of orbits, you think just gravity, gravity, gravity. But the Yarkovsky effect also affects these smaller objects that are close to Earth as well. So, in summary, radar is totally awesome. We look everything in the solar system, pretty much from Mercury, Saturn, beyond Saturn. It takes too long for a signal to get back. We do Saturn's rings, we do Jupiter's moons, we look at the charged particles in the Jupiter system. It's a much more inexpensive way of getting information about asteroids, planets, moons, than sending a spacecraft there. It's excellent for figuring out what the hazards are from space, what the risks are. Is it worth doing anything? It's really useful for space mission support. How big is this asteroid? What's the shape like? Where's its orbit? And you can also look at the whole population. We look at hundreds of these asteroids. You can start making inferences about what asteroids are like as a whole. You see all these diverse ones. Each one is very different. So you say, 14% are contact binary, 16% are actual binary, a very small percent are triple systems. So you can see how diverse the population is, but also what they have in common. So, thank you again for your time. If you're ever in Puerto Rico, come visit. If I'm not there, I'll get someone to show you around. And thank you for your attention this morning. Please ask me lots of questions.
So how often do you have situations where you think that there's an asteroid that's going to be coming dangerously close to Earth, or does that not happen? Or? Oh, yeah.
So on February 15th, February 14th, we all go to bed. There's this asteroid flying by the next day. And everyone's, Lonnie, are you observing this asteroid tomorrow? I was like, no, too low in the sky. We can't get it from Arecibo. And, a colleague is at the UN saying, we have impact hazards nailed down. We know where everything is. We've got this in the bag. And, they wake up that morning. It's like, there's been this bolide explosion over Chelyabinsk in Russia. And, it's knocked out acres and acres and acres of windows. People have been treating for flying glass. And, there's all these dash cam videos going around. So sometimes they show up and we have, no idea they were coming. That one was sort of small. Would have probably fit in this room. Maybe a little bigger. Maybe 2 school buses.
And it still did all that.
It still did all that damage. It's like, well, no one died. Like, yeah, this sucks that it's like minus 40 in Russia and you don't have any windows. And you see these videos, the security cam videos. There's the explosion, and you see these guys walking out of this kind of garage with a door, cutting the garage door to go check out what just happened. And as they're walking out, the garage door just falls down on the whole thing. It's like, this is horrible. But then one guy gets up, like, opens the door, slams it on the colleague behind him. It's just like, no one died, but still, this is this is awful. And apparently all these kids see the explosion in the school room, and they've been ducked and covered, and the teacher's like, okay, it's okay to get up. And they get up, and they all press themselves against the window to look at the fireball trail, and the shockwave comes, and that's how they all got injured by flying glass. So, like, no one died, but it's still hazardous. I mean, it could have been a lot worse. But, so those things happen that you don't know. So those are the unknowns, I guess. You know these things can happen. But there was one Apophis a few years ago, and I was like, oh my gosh, 2029, this thing's going to become nature's reset button. So every couple of years something comes along and people get really excited. But for the most part, you can rule out impact hazards. 2029, 2068, I think has been ruled out, and there's some vanishingly small probability in 2072 that it might hit us, but I wouldn't lose too much sleep about that. There are, it's not very often, and a lot of times when we do observe them with radar, you rule out impact for decades, hundreds of years. So it's a very good tool for that.
So if you find out, are there like supposed to be backup plans, like people you're supposed to tell if you find out?
Yeah, I went to one of those meetings in July. It was like, so there's this idea of this asteroid redirection mission, ARM. Like, we're going to take an asteroid in a bag and bring it home in a reverse, something retrograde lunar orbit. And astronauts.
They want to like orbit it next to the moon so they can study it up close.
Yeah, it's, and it's Gentry Lee, everyone's favorite 10 sigma curmudgeon technocrat and skeptic, is like, for no amount of money and no group of people on this earth can you do that these days. Like, you can't do this for $4 billion, get out. So there's this idea that you can redirect an asteroid as sort of practice for deflecting it eventually. And I think if there was like, hey, in 10 years we need to do this or else, you lose London or Denver, people would get on it. But I don't know. You publish it in the literature and everyone panics, and I think there are people who would be less panicked. And, hey, the government's shut down right now. I guess you better call up your favorite private space program and say, hey, you're still working, help us out. But also the idea of planetary protection and sort of anthropomorphizing asteroids is inherently dangerous. It's a very American, very frontier, very colonialist exploration narrative. And that might work for some of us in this room, but for other countries, it doesn't really appeal. So how do you discuss preserving life on Earth and collaborating to protect life on Earth in a way that other people are going to be interested, that aren't just Americans, sort of a cowboy problem? So how do you rally the troops? That's, you tell people, and I think there are structures in place. And FEMA is like, yeah, just tell us, and we'll do what we can if this becomes a problem. But there's not a lot of money right now for this sort of thing. And there's some international collaboration, but not necessarily a lot. If you hear Chris Lewicki from Planetary Resources talk, it's great. You're into rugged individualism and frontier and mining, but a lot of people aren't in this world. So there's also the salesperson and marketing job as well for planetary preservation of life. Other questions? Yeah.
We were at a messenger meeting like 2 weeks ago. They
showed overlays of the Earth-based radar. And I don't actually know if there's any people who go to maps with the ice on Mercury compared with the people map. It's amazing how well they find that stuff. And these maps from Earth.
Is it Nancy Hanover working on that?
Yeah, she was the one giving the talk, but yeah, it's pretty impressive.
It's really, like, just to see how well it lines up. And I think that's one of the strengths radar can really provide, is you can get kind of a shape where you can get scattering properties you can't get from optical, and you can combine it with other wavelength data, and you could do such cool stuff as a result. And for this QE2 asteroid, we're seeing sort of not necessarily differences across the surface, but as it moves out of the solar system, you're seeing completely different thermal behavior than when it was close to Earth. And so if you know the orientation of the asteroid, you can say, okay, then we can explain the thermal behavior. And also for Mercury, you can, it's another bit of evidence to back up what you've already seen in another wavelength.
Can you back up the gravitation level of this body? I mean, how small is it?
So this is 3 kilometers across. And it's 1 gram per cubic centimeter squared, or 1 gram per cubic centimeter in terms of density. So if you assume the sphere, pretty much, you can get the mass from that. They're not very massive. And the other thing is, if you had, they're dusty too. So if you go out on one of these asteroids, you're just going to be covered in dust from electrostatic forces. So can I borrow your brick-shaped asteroid? This is a brick-shaped asteroid. You're an astronaut walking along a brick-shaped asteroid. You are walking uphill if you're walking along this, because suddenly you have much more mass compared to here. So asteroids, when you get off the sphere, things are really weird. But a lot of them are sort of rubble piles, buried capsules, stuck together, more like electrostatic forces than gravitational forces. And so you might sink up to your waist if you're walking on an asteroid. It's a completely different gravity regime. Also, they're pebbles, so they act more like a powder. So if you ever opened a flour, you're trying to bake something and you get covered in flour, covered in powdered sugar or cocoa. It'd be the same thing, except you'd have pebbles on these asteroids acting the same way. So there are people doing research on the Vomit Comet, and also hopefully these suborbital flights once they start, on sort of how do you get these aggregates, these pebbles, behaving in microgravity situations like they would on these asteroids. And so when you plan to set an astronaut there, how's it going to behave? Are you going to stick up to your waist? Are you going to be able to walk on it? What's going to go on there?
You guys, this peanut shape ones, are they loosely round, just balls there?
Yeah, they're just touching. And sometimes you get sort of ponded deposits between them. But they're just touching and orbiting. Orbiting but touching. It's a wild world out there. Any other questions? People look happy, curious, something?
How many asteroids at any time are, I don't know, would it be orbiting or just flying by? Or I don't know if that's called an orbit when they just kind of.
So when they fly by, there's a couple of Twitter accounts. There's Low Flying Rocks, the Minor Planet Center, and Asteroid Watch, all tweet. This asteroid just passed Earth. It's this many billion miles. So a couple times a week, ones come by that are relatively close.
No. Are you randomly sending signals to see if something happens?
No, we are not a search facility, because you transmit, you wouldn't know when to receive. And we only have a 1 arc minute mean. So we don't have a huge search capability.
You
And
have to know the quickness of the asteroid before you do.
exactly. So we are sort of tracking them before they find us. But the optical telescopes are the one that would find these asteroids and get an initial of it. And we do improvement and shape modeling.
You get the call and then you try.
Yeah, so so mostly, you write a proposal 6 months ahead of time, 3 months ahead of time. It says, okay, we know where all these asteroids are going to be in the next year, and we're going to observe these 80 asteroids for the next year. And then also, once a month, we schedule an all-nighter to just observe whatever's up. So at New Moon, the telescopes in Arizona and New Mexico open up and they discover new asteroids. And so we schedule time 2 weeks after that when they'll be in the Arecibo sky to follow up on them to improve their orbit. So we observe things that we know will be detected, but we don't know about ahead of time. And then occasionally, there's a lot of asteroids that have very uncertain orbits, so we're not able to point at them because they're outside of our 1 arc minute beam. And so when the orbits get improved, sometimes we're going to call and say, hey, you should do this one. It just got better. I've gotten requests off Twitter actually, like, are you doing this object? Like, oh, no, it just got better in the last 3 days, and we haven't been sleeping because we've been observing, so we aren't quite aware of what's going on. So we've had those, and then every once in a while, NASA headquarters calls up and says, y'all should do this one. We say, yes, Dr. Johnson, we will. Especially requested by HP.
There was some news a few weeks ago that he was getting calls from the facility. I don't know if they're planning to retire, to upgrade it, or...
The NSF would love nothing more than for Arecibo to go away, because it costs about $10 to $12 million a year to run it. They want to hand it off to someone else. Cornell lost the contract 2 years ago to run it. So now it's run by an unholy commingling of SRI, based out of Menlo Park, USRA, Garibaldi Bandit in D.C., and a glorified community college in Puerto Rico running it. So having 3 partners running a facility like this is interesting. It works out somehow. But radar is now getting funded mostly by NASA rather than the NSF. So we're sort of keeping the observatory afloat in a lot of ways, and we're getting in more money and more people, whereas everyone else in astronomy is going nuts, losing money. Budget, the budget is going to be fund-sized for the next coming years, if it's sized at all, for planetary science. So the NSF, I mean, a couple of years, 2006, they wanted to close it down, but because of its ability to understand near-Earth asteroids, and especially for impact risk assessment, it's sort of invaluable, more than sort of invaluable in that regard. But the facility is definitely aging. There's been a lot of deferred maintenance. Every once in a while, it's like, don't take the cable car, don't take the catwalk. It's like, well, it's really easy to build things, I think, in general, but to get an operating budget and maintenance budget, people don't like to think about that. So when you're designing your systems, design them to be easy to maintain. Because, going forward, the Puerto Rican partner really wants to do the site planning. And, what does the observatory look like in 15 years, 25 years? Where are you going to get the money? But at least they're thinking about this. So how do you make it easy to maintain? You need fewer personnel. You need less money, so it's less complicated. How do you preserve science as you're thinking about this? If they're like, we want to build this planetarium and this and that, we're like, oh my gosh, RFI. Like, kill our ability to do science if they do all. They're like, oh, okay. Well, maybe you can move a visitor center into town, but how do you preserve science, but also sort of do more education, public outreach, in a way to get more people there, more money there, but keep doing science. So it's a very complicated, tightly coupled system.
Have you seen the movie Contact?
Yeah.
Arecibo was in the
Yep.
beginning of it.
I've stayed in one of the dorms that you see Jodie Foster hucking her bag
Nice.
up into. We also have a research experience for undergrads. I don't know if any of you are juniors, sophomores. So the NSF will pay you to go spend a couple months in Puerto Rico doing research. Pay for you to fly down there, pay for you to live there, and there are engineering opportunities as well as scientific opportunities, and also programming ones. So write interfaces, write code, help out with observations, and go hang out in Puerto Rico, all the pineapples growing. So there's definitely student level opportunities there as well.
How would we look for that then?
Go to the NSF website. I don't know if you're familiar with REU's.
Or USRA, USRA does that, or?
NSF does that. So it goes to the NSF. The NSF REU program is mainly, they have, and you can also, SRI has a REU. There's one, the Department of Energy has one at Stanford University that I did. There's one in Hawaii at the observatory there. And you might be like, science, like we need more engineers in science. We need people who can write code, who can build things. A lot, the science is sort of incidental, to pick it up on the way. But having a really firm background in engineering principles, processes, code, will this work? Will it break? These are really important things. So, that's a great place. And the RU is excellent. They take people all over the island. You go to San Juan, you go swimming, you go bioluminescent kayaking, you go on the littler islands, stand-up paddleboarding, hiking, waterfall. You don't have to shovel snow. In the summer anyway. If you like humidity, it's a good place. But yeah, thank you for your attention. I will be around until probably noonish if you want to come by me.